Okay. Hello. Let me check on the document camera. Okay. Okay. So let me check if this is focused correctly. But today I wanted to show zero knowledge proof in constant rounds without a row or CRS for, in fact, NP complete language. And right, because well, first we showed zero knowledge proof, which was either had weak soundness or was non-constant round for graph isomorphism, which we don't have polynomial algorithms for, but we also don't know if this is NP complete. Then we talked about languages in hold on. Sorry. I have to log off from. Okay. Sorry about that. So, and we talked about languages. We focused on languages of created by group homomorphisms that are very common in cryptography. But it is also good to know that, in fact, everything can be proven in zero knowledge, everything in NP. And these general constructions are feasibility results, but they are also, in fact, of interest from practical point of view, and which is surprising, perhaps, but true. As part of this, we should talk a little bit about commitments. So, as we saw last time, it's perfect binding versus perfect hiding, and also malleability issues. And some zero knowledge in practice things actually relate to this, and in particular, this has implications to zero knowledge proof security in concurrent setting. So in the setting where many people prove things at the same time to one another, and you want to argue that proofs made by all honest people do not reveal any information, but at the same time, all the proofs made by adversary are sound. And yes, so all the good guys, so to speak, their proofs can be simulated, but all the bad guys' proofs need to remain sound even during the simulation. And this will have, if, as we have seen last time, and we'll see again here in this zero knowledge proof, commitments play an important role in keeping people honest and forcing honest behavior. But in a concurrent setting, you will need these strong properties of commitments. We'll come back to them. Okay, perhaps we managed to see some other zero knowledge issues, but that's the plan. Okay. So let me focus. Sure. Okay. A few things about commitments, because we'll need them as a tool for this zero knowledge. So recall Pedersen commitment. So let's review some commitments we have seen. Right, the commitment, so there's parameters, which is G and H in a group. Commitment given these parameters to message M is G through R H to the M for random R, and the decommitment is the R, right? And the opening is just given the decommitment and the message and the commitment, well, you just verify that is right. And what were the properties? Perfect hiding. Yes, because this is a random group element independent of the message. And computational binding. The binding is requires discrete log assumption, right? Because if you can compute this discrete logarithm between these, then in fact, so discrete log between G and H implies a trapdoor, and we have seen that actually the fact that this is a trapdoor commitment that also has positive consequences, right? But it also has negative consequences, right? Whoever posts this CRS has a trapdoor that breaks the commitment property. Now, if you view of commitments in the CRS setting, that's the good, that's the one way to view Pedersen commitments. Someone publishes these parameters, then everybody else can commit and decommit, and it has these properties. But there is an interactive version in a zero knowledge proof, right? It doesn't have to be, the parameters don't have to be really announced beforehand. Perhaps in an interactive version, you have, well, party A and party B. And how about if the party A has to commit to something? How about party B generate the instance of a commitment scheme? So G is a generator of P order group. And let's say this generator is, well, everybody can verify that this is, generates a prime order group. This could be any point on a NIST approved curve, elliptic curve, but H is a random element from the same group. And now this guy A, well, he can commit to a message and then decommit. And if he tests the M, right, then this guy can verify whether this commitment and decommitment and the message correspond to one another, right? And the properties are preserved. So what could go wrong if the parameters are picked not by a trusted authority, but by your counterparty? So you are this guy, and you want to commit to a message. Well, binding is sort of not your concern, right? Because binding is the concern of B. It's a concern KA cheat by committing, quote unquote, and then decommitting to different stuff. Well, no, he can't under the discrete logarithm assumption, because B is the one who chose these parameters. So if A could cheat, he could cheat. Yeah, he breaks discrete logarithms assumption in the same argument. So what can go wrong for A? Well, hiding, right? Before we looked at the system as if these GNH were chosen by a trusted authority. Now they're are chosen by your counterparty, who might be trying to cheat you. The aspect that they're trying to cheat you is the hiding aspect, right? From A's point of view, it's the hiding that is a concern. But this is perfect hiding for all parameters. So A can verify that G generates a cyclic group, and that H is an element of the same group. And if so, then this is unconditional. This is a random group element, which is going to mask out completely that one, regardless of how B chose these two. Like, for example, B could have chosen them to be like equal. You know, he can choose them in completely arbitrary way. The only thing is that they both have to. So the only way that this can go wrong is if G is 1. So this way, this is not a random group element, right? It's just always 1, and it reveals H. But well, that's just an easy check for A, right? A does have to check that these two things generate the same group. In a, say, RSA case, where you have many subgroups of the n star, it is not clear how you can verify that two elements mod n generates the same subgroup, multiplicative subgroup, mod n. Perhaps this guy generates a very small subgroup, while this guy generates a large subgroup, in which case everything created this way belongs to the small subgroup and does not mask fully that value. In fact, in RSA setting, many times this has been, proposed by somebody who overlooked this, and it actually is insecure. Okay, so but in prime order groups, you can verify. NIST curves come with algorithms to verify whether a point is on the curve or not, and also with algorithms to verify that the curve really is a prime order group, and therefore has no non-trivial subgroups at all. Okay, the only subgroup of a prime order group is a trivial subgroup of 1. Okay, so this CRS business that we have seen, it actually goes away in interactive applications. Okay, but still you have computational binding. But we said before, we cannot achieve perfect hiding and perfect binding at the same time. This goes through for interactive commitments as well. We have also seen that any CPA public key encryption implies a commitment scheme with perfect binding and computational computational hiding. And again, we thought of parameters as a public key of an encryption, and commitment under these parameters as a random encryption under this public key of the message, and using some randomness, and the commitment is the randomness used in encryption, right? Which allows verification. Now, do you need these parameters to be trusted, to be picked by a trusted authority? Actually, no. A can pick the public key. So it's a public key generation, and in fact, it doesn't need the secret key, right? But of course, key generation does generate this, and he generates the commitment as a pair, the public key and the commitment to a message, and then the commitment is the randomness. So this is the commitment, and this is the decommitment, right? And whereas this was an interactive commitment, this is the non-interactive one. It remains perfectly binding and computational. Well, so that this is computationally binding follows immediately from semantic security of encryption. It is perfectly binding. That part uses non-standard properties of the public key encryption. So for this to be perfectly binding, you have to, the encryption, you see, normal use of encryption is that you're going to pick this the public key at random, and you're going to encrypt using true randomness. Now, the cheating interest is to cheat on binding of this. So perhaps there is some coins in the key generation that can create a key that looks like a normal key, but actually encryption on those keys is not unambiguous. In other words, a same ciphertext can be encryption of two valid plaintext. Perhaps on true randomness, this encryption should work, but perhaps on some, it works in some bad way. In particular, the badness that A is after, cheating A is after, is finding two randomnesses and two messages that collide, that create the same ciphertext. So that is not a standard notion of public key encryption that it would work for all things. First of all, B has to have some algorithm to verify that this is a valid generated key. In prime order groups, that is easy. In RSA, it is not. It is not so obvious how to prove that. How can anybody be convinced that an RSA modulus is correct? It's a really product of two primes long enough, right? Maybe it's a product of three primes. RSA security is based on hardness of factorization. So determining that it's a product of two primes or not is also hard. Is it now we can prove in zero knowledge that public key, RSA public key is generated correctly, but for these applications, that's a chicken and egg problem. Okay, let me come back to the malleability later. Okay, let's first, and I guess what also is good to say is that there's many good things to say, but one is kind of important for quote unquote practice. It's that random oracle model immediately gives you well, a commitment. Is it computational? Is it perfect? So it's perfect hiding and binding in a way, perfect, but only for computationally limited adversaries. So in what sense is it perfect? Well, if you believe that the hash function is a true random oracle, then there is no computational assumptions behind either hiding or binding. The only assumption is how many hash oracle queries can the adversary make. And as long as that number is limited, is polynomial, you get unconditional hiding and binding. What's this commitment? Well, very simple. Commitment to a message, in the system where a hash function is a so-called parameter, right? But it's really an oracle and not a bit string. Is hash. So I guess it should be written like this: the committing algorithm accesses hash function as an oracle. Is a hash on a message and a randomness for security parameter long random string. And the decommitment is the randomness, and the opener can take the message and the randomness, hash them, and check that it's equal to the commitment, right? In fact, it requires, it's the cheapest commitment, right? Because if you believe that SHA-256 can be modeled as a random function, then it costs you a single hash to commit, whereas here it costs you a bunch of exponentiations, and so did here, because this is a public key encryption, and likewise for the verifier, right? So this is, several orders of parameter faster. And in most systems where you would like to implement this, at least for now, you would go for this implementation. So quickly, why is it hiding? Well, because if H is a random oracle, right, and I give you this commitment C, the receiver can query the hash on any message, on and on. But he would have to, the only way to figure out what the C corresponds to is to hash exactly on the string. And given that R is random, and as long as the security parameter, there is number of queries over 2 to the security parameter, probability of B hashing MR, right, on a given C. So if B has only the commitment, there is negligible probability that he will find the pre-image. Okay, and if he doesn't, there's nothing that this tells, right? This is information theoretically independent of everything he sees. Likewise, binding. How can this guy decommit in 2 ways? Well, he queries the hash function, and what's the only case which is allowed, which allows A to cheat? Well, he needs to find M1 R1 and M2 R2 that hash to the same value, right? Then he can create a quote-unquote commitment, which will have 2 different openings. But that probability is likewise k over, well, actually it's k squared over 2k, right? Because he can query, and it's a birthday bound that there is going to be a collision in the hash function, right? So So, but this K was the size of the randomness, and this case is the size of the H output. So in the SHA-256, this is 2 to the 256, right? So even if this is 2 to the 60, then you set 2 to the 120 over 2 to the 256. Yeah? So that's good. Yeah. Okay. So let's go to the proof for an NP complete language. Will not go through the whole proof, well, we'll show the proof, but will not prove that the proof is zero knowledge. We'll just sketch why it is so. So, so zero knowledge proof for three colorability. So the citation is Goldreich, Kahan. And here's how. First of all, what's the tricolorability, right? So the language is of graphs such that G is tricolorable, i.e., there is a permutation, there is a labeling of graph nodes. So these are nodes of the graph to three colors, 0, 1, 2, such that for all ij which are edges in the graph, phi of I is not phi of j. Yes. So you can label all the graph nodes with colors, three colors, in such a way that every two nodes which are connected by an edge have a different color. And it is NP complete. So there is no, first of all, okay, so it is in NP because if you guessed the coloring, right, you can verify it easily. It is NP complete. In particular, the reduction is from 3SAT. So if this was solvable, then so would 3SAT be, because you can embed the 3SAT clauses into a graph such that if the graph is colorable, then every clause is becomes correct. Okay, so it's if you don't remember, it's a good sort of mental puzzle how to do this embedding. But given that you know it exists, it's already you know, at least halfway through to actually finding it. Okay. So Goldreich-Kahan proof, zero knowledge proof for graph colorability works like this. So the prover has a graph and a coloring, right? And the verifier has the graph. So let K be a security parameter, and we'll see later what it should be set for. This guy picks for I, which is 1 to K, pick edge pick an edge. Okay. EI in the set. Okay, so let's call this edge NI, MI. Yeah, these are two nodes in the graph, and we okay, which is an edge set of the graph at random. And you're going to pick k of such edges. Send a set CI of commitments to these edges, okay? And I goes from 1 to k, okay? Now, this commitment is a perfect hiding commitment. So the way we implemented it here, this was a perfect hiding commitment without a CRS if it was interacted. So actually, it's the party who receives this commitment has to pick this parameter commitment instance. So this would actually mean that the prover here picks the commitment instance, the commitment parameters. Okay, and so this is a perfectly hiding commitment. Okay. Now,
Professor?
Yeah.
Do we need a new instance for every commitment, or can we use the same CRS? Because our definition was.
But, I think that one instance works actually.
Okay. Yeah, because our definition of security was using one only, right?
Say it again.
Our definition of security was using one, just one commitment.
Yes. So, but you know, if you think of this interaction as this guy chooses one instance, and this guy commits to many things, sends many such commitments, then all of them are perfectly hiding, and all of them are computationally binding. So there is no problem reusing this commitment instance in that interaction. Right. And you can probably keep this and have this, you know, not even like in a single round, but he can commit and commit and commit throughout some protocol to be, and they will all have these properties.
Okay, thank you.
Okay, and now hold on a second, I'm blanking. Just okay, he picks a random coloring. So k random coloring. Yes. Again, for I equal 1 to k, the prover, so far he sends a commitment instance and gets these commitments, doesn't do anything with them, but keeps them. For I from 1 to k, the prover pick a random relabeling of coloring phi, call it phi I. Okay, so phi I is another function that colors all elements, all the nodes. But that function is just a permutation of this one, right? So it's the same coloring, but just we're going to randomly relabel the 0 color as either 0 or 1 or 2. Okay, so well, with 1/6 probability, it's the same coloring. Yeah, because there's 6 ways to permute 6 or something. Yeah, I guess so. Okay, and what he will send here is the set of commitments. So for all I 1 to k, he will send a set of commitments to phi I of n for every n in the set of nodes of the graph. Okay, so he does it k times, but each time what he does is that he commits, oh, sorry. Okay, I lost the commitment part. Okay, so what he sends is the set of commitments. So now commitments from the verifier were called C. So let's call the commitments from the prover C prime, or actually C hat. So these are C hat N is the commitment, but we'll use a different commitment scheme, com hat, on the coloring of the nth, the current coloring using the coloring phi I of the node n in the graph, and that I will send you a set of such commitments for every node in the graph. And very basically, well, let's just not have a nasty notation, but just says that this is for I1 to n, if to k, sends such a thing. Okay, sends the set of commitments for every I. Now what? So this guy committed to and basically verifier committed to an edge, to a random edge in these k instances. This is really a parallel repetition of a proof. If you forget about the index I, okay, the basic proof that happens is that this verifier commits to an edge, and the prover commits to a random relabeling of all of the colorings of all nodes. Okay, and this happens in parallel for k times. Okay, there's k instances of that. So this guy is going to now open all CI commitments. In other words, sends the decommitments and sends the actual edges which were committed here, right? The prover verifies the CI decommitments that were sent here, and if they're all correct, okay, if the verifier indeed opened all these commitments, then he has to, for every instance I, the prover has some edge chosen by the verifier. He needs to, for all I, open open C N I and C M I for so the verify CI, so open all C commitments, open to what? To some set of EIs, right? So what if the ith edge is NI MI, then the prover is going to open the commitments to the coloring of these two nodes. This shows what? This opens to phi I of Ni, and this opens to phi I of Mi. In other words, there are two, the graph, the edge that was chosen by the verifier on that instance is an edge between Ni and Mi, and the prover decommitted to the labeling of the two nodes. So what does the verifier do? He accepts if all decommitments correct. Verify. Okay, and moreover, the labeling of these two nodes is indeed different. And that's it. And it's a 5-round proof. Now that this is complete, so it always works if there are two honest parties that behave honestly, right? This, okay, it's true. Now, what about soundness? So how can let's say the graph is not colorable, okay? Then a single instance of this proof, forget the commitments for now. Let's just think of the 3-round proof where the prover commits to relabeling of the coloring for every node. The verifier chooses one edge, and this guy has to open these commitments in such a way that that they are indeed, the coloring is different. If the graph is not tricolorable, then there is no way to create these labels which will have this property for all edges, right? Because if it has this property for all edges, then it's tricolorable. So there will always be at least one edge which is labeled wrong, which is labeled by the same color, whose nodes are labeled, whose end nodes, right, are labeled by the same color. So if commitments are all perfect, okay, so they basically work like black boxes, and there's no way to cheat in any way or fashion, then probability of V accept on graph not in the language is the probability of finding so it's at most 1 minus 1 over n squared, okay, where n is the size of the graph. Yes, because this is the upper bound on the number of edges, and there is at least one edge wrong. So if yeah, you can pick the bad edges, but there is this chance of picking the correct one on which you will discover that the prover is cheating. So that's for a single instance in one instance of this proof system, right? Now, if you repeat this k times, k repetitions drives this down to 1 minus 1 over n squared to the k, right? And setting k n cube would mean that this is close to epsilon 2 minus n. Yeah. Yes, because using the 1 minus x to the x is as x grows, this tends to inverse of e. Yeah. So which is negligible. All right, so you can repeat it polynomially many times, and you're going to drive down this 1 minus non-negligible into negligible error probability. Yes, soundness error probability. So it has negligible soundness if repeated polynomially many times. Now, what about the commitments? So can the prover cheat in commitments? Notice, okay, so first of all, what property here? This commitment has to be perfectly binding. Because we are in the business of zero knowledge proof, not a zero knowledge argument. So we want to show that unconditionally there is no cheating strategy. Okay. Again, in practice, we might zero knowledge argument might suffice. It's just that they are harder to work with, and it's nice to not have to worry about cheating of the prover, and has other consequences. Existence of such of unconditional soundness proof systems with zero knowledge. So this has to be perfectly binding, but you remember we had commitments for both sides. Okay, if you want a perfectly hiding commitment, you have it. If you want to have perfectly binding commitment, you have it. So because these commitments are perfectly binding, there is no cheating strategy for the prover at all. He has to commit to some to the labeling, and cannot open differently from the way they were committed. So he cannot open based on knowledge of which graph, of which edge he has to open. Right at this point, without knowing anything, he had to commit to all these n square to n labels. Oh, yes, so that is still n square because I have to choose the correct pair. Now, what about this? The fact that the prover, in fact, knew about, he had some, okay, he had commitments to all these edges. So perhaps he could have used the information about the edge that the verifier is going to eventually reveal here to create these commitments in some cheating way. But no, because they were perfectly hiding. So this is information theoretic independent of the edge that the verifier really is going to pick. That's why both of these sort of put in a correct angle direction, the properties imply what we want. Now, about zero knowledge. Well, here is this is the proof system. Yes, and let's argue that it is zero knowledge, and we'll just sketch this. But you will see, well, a case that we have seen in the simpler case of the 3 rounds zero knowledge proof in a CRS case. It's a case. It's a rewinding strategy. So a simulator having just a graph, right, and no coloring. What can we do? Well, as in the case of that 3 round CRS proof, first of all, pick randomness for V star. Okay, call it RV. All right. So the verifier, even malicious one, is from now on going to be fixed and deterministic. Okay. Do the send the com instance. So perform this commitment preamble. Now v star has an input G and the fixed randomness. So he's going to send the CIs, right? Okay. Now at this point, compute C ends, the C hat ends to be commitments to random stuff. Okay. We are just at first, because we don't know, the simulator doesn't know coloring, cannot find the coloring. And clearly is not going to find a coloring which can be opened in a good way with, so, and this goes, you know, for all I, right? And this is also, so for a single instance, he would survive it with a probability very good. But on parallel instances, he cannot survive this, right? This is the soundness argument. So let's not even try. Let's just commit to garbage. Now, let's say that this guy does open openings of the CIs. Okay. If openings correct, then at this point, the simulator knows all the EIs that were chosen in these commitments, right? So now the simulator knows which edges the verifier it has picked and committed in here. He cannot create the correct openings, but that's okay. At this point, rewind V star, i.e. run V star on GRV again. Feed him the same com instance. So this com instance is chosen by the simulator. Sim chooses random commitment instance. But okay, run again on same commitment instance. So there's two things that are reused: the randomness, this one, and this one. Okay, that was chosen by the simulator at the beginning, reused in the second execution with this V star. Now, because V star is deterministic after we fix this randomness, and because we are reusing the same instance of the commitment scheme, well, he sends the same commitments. And now, so commitment instance is same. Yes, V star on GRV sends the same. Same. Yeah. And now the simulator knows what the EIs are. Okay, so now he can simulate. Pick for all I, the CNs, okay, which for that instance I, are basically, you know, this could be commitments to random stuff for all nodes except nm that is equal to the where's my EIs here, right? So for all nodes which are outside, so for let's say okay, I want these commitments to be such that the commitment for all I do this, commitment to n is a commitment to a random color. A commitment to m is a commitment to a random different color. You have 6 choices here. And commitment to any node, let's call them x, is a commitment to a random stuff for all x is different from n or m. And what n and m did you choose? The n, m form the edge EI. So now when this guy, so that's how you are forming these commitments, okay? And you're doing this for each instance I. When this, the verifier, hold on a second. Where the verifier, again, like here, says openings of his initial commitments, if correct, then now we can decommit, because we just need to open the commitments to the edges which form EI, right? So we will only need to open these 2 commitments. Open Cn and C hat m for nm equal EI, and do that for all I. Yes. So assume that a malicious verifier is such that it's a case of an algorithm that if he sends some commitments, okay, in the second round of this proof system, then in the 4th round he will decommit to them correctly. Okay, so in other words, this if opening correct and if opening correct, these are always true for that case of V star. Then what commitment did we use here? The perfect binding one. Okay, so oh no, sorry, here okay, now consider a V star that doesn't break binding of this commitment instance, and therefore openings here and openings here are the same. Okay, the EIs here and the EIs that were open in these 2 executions, right? So the com instance and the RV are chosen, okay, at first. And then there is the first what was the remaining randomness? It was here. The Cn randomness used in these, and we either had opening to some set of EIs. And then we ran this again, using a new commitments from the prover. This time, not all garbage, but mostly still garbage, but at the edges that we knew that the verifier, or hoped that the verifier will open, these edges, the nodes on those edges were correctly set. Okay, so that they will eventually verify. The openings of those will verify, right? So we created CN, correct on EIs. And here he, again, the verifier opened to some EIs prime. Now, if EIs prime and EI are the same, this goes through, right? And it is a little complicated to see that this run of the algorithm is distributed as exactly as the correct run. Well, is it exactly? Not exactly. It is a case of rewinding. So is this okay? I think this is not a perfect zero knowledge. It's computational zero knowledge, maybe statistical. I'm not sure if this is distributed exactly like a random execution, or just indistinguishably from it. Okay, but this worked under the assumption that the V star cannot break, that EIs here and the EI primes that were open here are the same, right? Because if they're different, this simulator gives up, right? He committed to random garbage here, so with high probability he cannot open if EIs somehow are different than those. Now consider that case of V star that breaks, that basically EI primes are different from EIs. Well, then you can see the reduction to binding of this commitment scheme, right? Of this commitment scheme, because this guy clearly sent some commitments, and then in one execution opened them this way, and in the other opened them this way. So this implied the set of CIs, right? They were fixed in this execution because they were just a deterministic function of the stuff. So this opening and this opening is two openings of the same set of V stars commitments sent in the second flow. So if they are different, then you reduce to a binding of a commitment scheme. That commitment scheme was perfectly hiding, but computationally binding. So that reduction is at most, that works only for efficient V stars. And there is a negligible chance that the V star will cheat, right? Because let's say that this is this Pedersen commitment based on DL. There is a negligible chance that the DL breaking algorithm works and allows you to find a trapdoor, at which point you can easily, quote unquote, commit to stuff and then decommit in very different ways. But that event has no negligible probability under the assumption that, that this commitment was computationally binding. And that translates into a negligible probability that these two are not equal. So EI are not equal to EI primes with negligible probability that is the same as COM binding, probability of breaking the commitment binding. Because there is this negligible probability of a difference, that will translate into the transcripts generated by the simulator at most negligible, but still negligible skew from the distributions that an honest prover would create. And yeah, so that's the sketch of the proof. Do you guys have questions on this? Okay. Let's I wanted to touch on this malleability and security of zero knowledge in a concurrent setting as a consequence. Commitment malleability and concurrent zero knowledge proof security. Okay. So, well, here is an example of a commitment malleability issue. In different, whether you have a commitment in a CRS or a commitment that is interactive, non-interactive, they all will have versions of this issue. So when so here is the basic question: if here is an adversary, the game here is the non-malleability game. The game commits to some value. At that point, the attacker should not, by hiding property, should not see anything, could not derive any information about M, seeing just a commitment. But let's say that he also commits to something. Well, by binding, this should commit attacker to some fixed value. Let's say now that we open C, and now he opens C prime. Two questions. Well, was A committed to C to some value? So this was open to M, and this was open to M prime. Was A committed to M prime at this point? Well, if we or could C prime be a function of C? And when without this decommitment, A couldn't decommit to C prime in two ways, or perhaps not even any way. But after seeing the decommitment to M, A can open decommitment of C prime, and M prime actually dependent on M. This is if M prime cannot depend on M, then we say that commitment is non-malleable. So this is the non-malleability property of commitment. Okay. Now, this is compared this to non-malleability of an encryption. Let's say that the public key, so this is non-malleability of public key encryption. Let's say that there is a public key and a ciphertext, which is an encryption under the public key of some message. And by semantic security, adversary does not learn C, does not carry information about M. But what if adversary could ask ciphertext and get back decryptions of the ciphertext? Does he now, can he get information about M? Now, this is non-malleability is the same as CCA security. So you might remember from the basic crypto that which no isn't that basic really, is that excuse me, that the attacks on CCA security of encryptions were through malleability of ciphertext. If it was possible for an attacker to take a valid encryption and transform it in some way, I didn't know what this transformation encrypted, but if the encryption was malleable, the decryption, the plain text hiding in C prime was related to the plain text hiding in M. And therefore, information about the M prime actually gave you information about M. Okay, and that was a break in CCA. Any encryption that has this malleability property would attack CCA. And but actually, the connection is even only if an encryption that is CCA is non-malleable. Well, this is not a formal definition of what non-malleability is, but basically, just like in this case, the question is there some non-trivial relation R such that the probability that M and M prime belong to this relation is different than the trivial one. Okay, so trivial relation, okay, is something that holds for random messages. Okay, so let's say M is chosen at random from the message space here, and even if you don't know anything about M, you can pick a random M prime, and there is some trivial relation like M equal M prime, which has a trivial probability of 1 over M. But an attack on non-malleability means that you pass this game for some non-trivial relation. And let's say it's the same for public key encryption. And you can see that this intuition of a relation between non-malleability and CCA security goes both ways. Okay, if you cannot create C prime based on C, such that M prime encrypted here has any non-trivial relation to M, then these decryptions do not help you in breaking semantic security of the ciphertext. Now, why is this? So the random oracle model commitment.
Professor?
Yes.
So this equivalence with CCA and non-malleability would be in the case that we already CPA, right?
No. What do you mean? No.
I mean, like, if you have a CPA encryption, then non-malleability is equivalent to CCA. But is that more general? It's always true?
Wait. So
because I remember we proved it for CPA, but I don't remember if it was
but what
true
do you
always.
mean? What did we prove for CPA?
So let's say we start with the CPA encryption scheme, PKA.
Yeah.
Then being CCA is equivalent to non-malleability.
Yes. Well, so non-malleability implies CPA.
Oh.
Because if you can basically get information about the message already from the ciphertext, then in a sense, like trivially, you can encrypt a message that contains, whose plaintext contains that information, and we win the non-malleability game. So non-malleability implies CPA security, but actually it implies CCA security.
Okay, I see it. Thank you.
So random oracle commitment, right? Commitment is a hash of the message and a randomness is non-malleable, right? Because if I send you a hash of the message and you have to send another hash, if I give you MR here, and you have to find M prime R prime, such that first of all, hash of M prime R prime is C prime, but also some non-trivial relation on N and prime holds, right? You can see easily in a random oracle model that you cannot win. Okay, that there is like Q over hash size chance that you will find that again, the only way to make anything correlated is, well, there's a trivial way. You replay C prime is equal to C, so we have to make the non-trivial requirement, right? Which in all these games, that the only way to make some so if you didn't hash, if you don't know the pre-image of C prime in a hash function, then it's a negligible probability that you will find it after sending it. And if you know the pre-image, the chance that you found any that is this one, right, is negligible also. Okay, so this not only is super cheap, but it's also is non-malleable. But see, if we try to do this without random oracles, it's well, non-malleable public key encryption implies non-malleable commitments, but they are the not perfectly hiding ones. And if the commitment scheme is the key in a ciphertext, okay, and now this guy chooses his key and ciphertext, then it's really non-standard properties of encryption, because any normal properties of encryption talk about the single key. Okay, it's not about me picking one key and encrypting something and you picking another. Okay, so you it doesn't generically follow from properties of encryption, but nevertheless, even like construction of this commitment scheme, if you want, if you're okay with computational hiding, you can do this. For perfect hiding, it's harder. An example, Pedersen commitment. Pedersen commitment, it is malleable. So think of the parameters in the CRS, and this guy sends GRHM, and this guy sends C prime, which is C times H to the delta. Yeah, and you can see it straight away. This guy opens MR, and right, so this is the commitment, and this guy opens M plus delta NR. Yeah, and it works, right? Well, maybe you can catch him like, hey, he used the same decommitment, the same randomness as I did. Maybe I will say, oh no, I don't accept that, right? In any application like this. Yeah, but this is not a big deal, right? Just do this, and now this becomes that. And if delta and delta is whatever you want, and sigma is random, then this is now random and independent of R, and this is whatever shift the attacker wanted. Okay, so it's clearly it's clearly malleable. So maybe, okay, we're out of time. Construction of non-malleable commitment scheme with perfect binding, they exist. It's a nice puzzle to follow up on and see. That's one thing. Another is that, okay, very quickly, what does it have to do with concurrent zero knowledge security? Well, basically, we have seen, except of the random oracle constructions, that commitment is an essential tool in creating zero knowledge. Okay, and you can also think of the random oracle as a form of commitment. If you bring, let's say, this proof system, where well, here you explicitly have a proof system where the prover commits and also accepts commitments. So, but the instances were different. So these were, I mean, even two independent commitment schemes, not just instances. But let's say that you use the commitment to commit to first messages in a so ACC is a Sigma protocol for language L. Yes, this HPCK with special properties, and we argued that Z plus the commitment to A, that this is that this was a 3-round full zero knowledge proof, not just for honest verifiers in CRS, where the CRS string is a commitment, is an instance of the commitment scheme. It's a commitment scheme. Okay, so this was both sound and simulatable. Now, in simulatability, required trapdoor for the commitment scheme. So the only way to simulate was if the simulator knew the trapdoor. Soundness, so simulation, so zero knowledge. Soundness relied on hardness of computing trapdoor from the commitment instance. The two stand in opposition to each other. Why is this a problem in a concurrent setting? So imagine that you have good guys and bad guys, okay? And they're running these instances of commitments of a proof system. So the good guys are proving something to the bad guys. But the bad guys are also proving their stuff. So they're sending their commitments, getting the challenges, and opening those commitments. I'm sorry, I'm running a little late, but I hope you can bear with me. It's just a few, 2 more minutes or so. And now we want soundness of, so we want two things go. All ZKPs by good guys, good players, are zero knowledge, so simulatable. All zero knowledge proofs by bad players are sound. Now, if you have a proof of simulation of zero knowledge that required you to hold the trapdoor for the commitment scheme, so the only way to simulate this, this is announced CRS generation, right? And everybody slavishly follows these parameters. Simulation required the trapdoor. Then how can we argue that in the presence of the simulation, the zero knowledge proofs that the bad guys do are still sound? If the only argument we had about bad guys managing to prove something incorrect was a reduction, that if they are able to do this, then that we break some computational problem. What problem? Well, that was the problem of, in that case, basically finding the trapdoor for this CRS. But we already have that trapdoor, and we need it for these to simulate these proofs. This is indeed very similar to this case. The good guys are doing something, adversary is sending something potentially related. We open, he opens. Is it for sure the case that his stuff is independent from ours? In other words, can he replay our proofs, mold them, and mold this, and mold that, so that this is actually all wrong? But because it's based on this stuff, it just is, if this is correct, because in simulation it is, this stuff that bad guys do based on what the good guys do, that is derived from them, actually goes through. And if you remember this proof system, this was indeed our example was GH, and this was the commitment was G to the A, H to the R, right? If you instantiate it with the Pedersen commitment, which is easily malleable, this malleability in fact will show you that this proof system does not have simulation soundness. If you simulate, the bad guys can make anything based on the simulated proofs, and they will be verified. And if the simulator started, because simulator does it for any statement, well, the bad guys will follow on some other related statements that are that can be bad, that can be outside of the language. So it's not hard to generalize it, and once you instantiate, you will see that this is possible. Okay. This kind of non-malleability attacks are, you have seen this in the basic crypto, in the all over the place, right? Of can signatures issued by the good guy enable the bad guy to issue signatures on something related? Can decryptions of some ciphertext can allow to find information about the challenge ciphertext? All these were already part of the basic crypto concerns. They are all the more pertinent to protocols where we want to run a protocol where we have some security argument for why the good guys protect their information, like, for example, the zero knowledge proof case. It's simulatable, and therefore, whatever good guys perform zero knowledge proofs on, it remains hidden. But in the meantime, the bad guys proofs must still hold. Okay, and I want both things to be true at the same time. And it's not so obvious, once you start instantiating these things, right? Okay. Multi-party protocols next time, and thanks for your attention. Of course, if you have questions, let me know. Okay. Okay, so I'll see you Thursday.
Bye.